Here I would like to talk about the charging capacitor, charging a capacitor. In order to charge a capacitor, I take a circuit of a resistance and a capacitor. And as you see, we have to use a battery EMF with a resistance and a capacitor. You know, at initial time, at time t equals to 0, we have Q equals to 0 at the capacitor, where Q at time t equals to O equals to 0. First of all, I want to calculate the current, the charge per unit time, the value of charge per unit time. I want to calculate the current per unit time, and also I calculate the voltage at the capacitor per unit time. Okay, and after we can draw the evolution of Q in terms of time, and also the evolution of the current in terms of time. Let me uh, let me apply the loop rule here. Let's say we have the circuit is connected to the battery. So here we have A, B, and here we have C. So here we have C, A and A, the same point, A, B, C, C. Okay, and after we come back to A. Okay, you know the summation of delta V equals to O equals to delta V CA plus delta V AB plus delta V BC. So we start with C and we finish by C. Okay, you know the current must be out of the positive side. So here we have I, and the current will be in this direction. Okay, you know delta VA CA equals to VA minus VC plus VB minus VA plus VC minus VB. Here we have plus and minus. Here we have the positive side. We have plus, okay? The positive side will be plus. And here we have minus, okay? We start with VA minus VC. VA, between A and C, we have the battery. VA here is at the positive side, so we have plus E. VB minus VA, so I take this resistance. VB is at the negative side, so we have minus the voltage at the resistance will be IR. VC minus VB. VC minus VB, V of C, here we have C, is at the negative side. So we have minus the voltage at the capacitor. You know, the capacitance equals to Q divided by C, by V. So V equals to Q divided by C. Okay, so we have Q divided by C equals to 0. So we get this relation, E minus IR minus Q divided by C equal to 0. Okay, and you know here that I equals to dq divided by dt. We can substitute the value of I here, and we can simplify the relation. Here we can put minus, plus, plus, and we put this term here. So we get IR plus Q divided by C equals to plus E. I equals to dq divided by dt times R plus Q divided by C equals to plus E. Okay, here I want to write the boundary condition. At initial time, at t equals to 0, we have Q equal to 0. Okay, at the capacitor, we have Q equal to 0 at initial time. And also at initial time, at t equals to 0, here, you know, so let me write here, at time t equals to 0, we have Q equals to 0. We don't have any charge in the capacitor. And also, if Q equals to 0 at initial time, R times dq divided by dt is I equals to E. So I equals to E divided by R. These are the two conditions at t equal to 0. Okay, the first condition. The second condition, when now I take the condition at time t where the capacitor is full. So we have a maximum quantity of charge at the capacitor. At this time, where we have Q max, at this time we don't have current in the circuit. So here I equals to 0. At that time where we have a maximum value of Q as the capacitor. Okay, so at this time we can calculate Q max. If I equal to 0, we come back to this relation. I equals to 0. In this case, we have E minus Q max divided by the capacitance C equals to 0. So in this case, Q max equals to C times E. Okay, This is the condition at the time t where we have a maximum Q and zero current, and this condition is at initial time t where we have Q equals to 0 and we have I equals to E divided by R. Okay, these are the conditions. We come back to this relation, to this one. You know, I want to simplify the calculation. Uh, we can divide by R. We get dq divided by dt plus q divided by rc equals to E divided by R. Okay, and we can put this term at this side. We get dq divided by dt equals to E divided by R minus Q divided by RC. Okay, this is the relation. Now I want to calculate Q. Okay, so what I do, here we have dq divided by dt equals E divided by R. We can multiply by C and we divide by C minus Q divided by RC. We take a common factor RC. So here we have epsilon or EC minus Q. Here we can take a common factor minus, so inside we have minus EC plus Q. Okay, we can write minus RC, we can change by Q minus EC. Okay, look here, dq by dt equals to minus Q minus CE divided by RC. The goal here is to put dq divided by Q minus CE at this side. Okay, so what we have to do, we put this term down here, and dt we put it up. So here we have dq divided by dt. Okay, so dq divided by, I put this term down, we get Q minus EC equals to minus dt divided by RC. Okay, this is the final relation is here. Okay, now I have to calculate Q. In this case, we put the integral on each side. We start with a time t equals to 0 to the time t. Okay, from this condition to this condition. This one at time t equal to 0, and this condition at time equals to t. So, and the capacitor will be from 0 charge to Q charge. Okay? It can be Q max or any value of Q. The aim point here is to charge the capacitor with a quantity Q, and we calculate at the end Q in terms of T at any point, so at any time. For this, I take between 0 and time t. Here, what we have to do to solve this integral, we can take u equals to q minus c e du equals to dq. So we can write integral of du divided by u, which is equal to ln u. We put u by its value, we get ln q minus c e, and the limit between 0 and q. So I am calculating the value of this integral. So we get here ln q minus ce minus ln q equals to 0, we get only minus ce. Ln a minus ln b equals to ln a divided by b. So here we get ln q minus ce divided by minus ce. Okay? So we can write ln q minus ce divided minus ce equals to minus t divided by r c. Ln a equals to b, so a equals to exponential b. So here we have ln a equals to b, so a equals to exponential minus t divided by rc. We can write q minus ce divided by minus ce equals to exponential minus t divided by rc. So q equals to ce 1 minus exponential minus t divided by rc. This is the value of q in terms of time, which is equal to ce 1 minus exponential minus t divided by rc. So here we have the value of qt equals to ce times 1 minus exponential minus t divided by rc. If we plot here q in terms of time, at time t equals to 0, at this point, we have qt equals to 0 equals to ce 1 minus exponential 0 equals to ce 1 minus 1 equals to 0. So at time t equal to 0, we have q equals to 0. What about at time equals to infinity? You know, at time equals to infinity, the capacitor will be charged to q maximum. So q at time equals to infinity equals to c e 1 minus exponential minus infinity. You know exponential minus infinity equals to 0. So here we get c e q at t infinity. As you see here, when we have that time equals to infinity, we reach the saturated situation where we have q maximum, which is equal to c times e. Okay, now I want to calculate I. You know, I equals to dq divided by dt. We have the value of q. We have to do the derivative of q. So I t equals to d divided by dt c e minus c e exponential minus t divided by r c. Okay, this one is constant. D of constant divided by dt equal to 0. So here we have 0 minus. If we have u equals to e ax, u prime equals to a exponential ax. Okay, so here we get we have minus ce. We get here minus ce times minus 1 divided by rc times minus equals to plus divided by rc exponential minus t divided by rc. We get c and c. The final value will be e divided by r exponential minus t divided by rc. This is the value of the current at the time t. Okay, we can plot here I in terms of time. You know, at initial time, the current must be maximum. Okay, we have I maximum. At time equals to infinity, the capacitor will get a maximum value of Q and I equals to 0 in the circuit. Okay, it's very important. At time equals to infinity, we have a maximum charge at the capacitor and we have a 0 current in the circuit. Okay, so we come here, we say at t equals to 0, we put here t equals to 0, the answer will be e divided by r exponential 0 equals to e divided by r. So at time t equal to 0, we have a value of I equals to e divided by r. And at time equals to infinity, I equals to epsilon divided by r exponential minus infinity. Okay, exponential minus infinity equals to 0. So I at t infinity equals to 0. As you see here, it's very important to know how you can plot Q in terms of T and I in terms of T. Now I want to calculate the potential of the capacitance. Okay, you know the potential uh, at time t equals to infinity. Let me come back here. When we have time equals to infinity, so I equals to 0. In this case, at time goes to infinity, I equals to 0. So V at the resistance equals to I R equals to 0. So we have only at the end V, you know, the summation of V of the potential equals to the potential at the battery. Here we have E, and we come here at T infinity, here V at V at the resistance equal to 0 here. So we get only E equals to Q divided by C. We have only the voltage at the capacitor equal to the voltage at the battery. In this case, we don't have any voltage at the resistance. Okay, so we can calculate here. We can calculate the voltage of the battery, which is equal to the voltage at the capacitor. We come back. So the voltage at the capacitor equal to the voltage at the battery equals to Q divided by C. We put Q here. We have the value of Q divided by C. We can eliminate C and C. We get finally E times 1 minus exponential minus T divided by RC. Okay, so we come back to the condition at T equals to 0. If we put here T equal to 0, we get 1 minus 1. So V equals to 0. Okay, here we get V equals to E 1 minus 1. So V as the capacitance, as the capacitor at T equals to 0 equals to 0. Okay, we don't have any voltage at the capacitor at initial time. And I, we calculated I at initial time, which is equal to E divided by R. At T infinity, we calculated the Q, which is equal C divided by E. And at T infinity, here we have E 1 minus E minus infinity, which is equal 1 minus 0. So V as the capacitance at T infinity equals to E. So the voltage at the capacitor at T infinity equal to the voltage at the battery, as you see here. Okay, and also at T infinity we don't have current. Now what about at T equals to R times C? This is the time required to charge the capacitor. T equals to R times C. In this case, we can calculate Q if T equals to RC. Q, after calculation, we get this time needed to charge the capacitor, and we get this current value at this time. Okay,